You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
Last time on Why This Universe, we talked about the conditions necessary for life to evolve on another planet. And we talked about the search for exoplanets in the Milky Way galaxy that could possibly contain life or be similar to Earth. But in that episode, our definition for life was really broad. Like, searching for life in the Milky Way galaxy could mean searching for anything as simple as, a single-celled organism. But while bacteria and microbes might be interesting to you, and, no shade if they are, nothing would beat discovering intelligent extraterrestrial life, like aliens as smart as us, or maybe even smarter. So today we're going to focus on the prospects of intelligent life in the universe. And we'll address this question of, if there really are as many exoplanets out there as we discussed last week, why have we not seen any intelligent aliens coming by? Why has no one tried to communicate with us yet? So if we want to figure out a good way to search for intelligent life in the universe, one thing we can do is to turn the camera around back at us and ask, if aliens pointed their telescopes at Earth, what would give away the fact that there's intelligent life here?
It's hard to imagine them being able to build a telescope where they could see our cities or really any of our other activity, but we're dumping tons and tons of electromagnetic radiation, light of various kinds, into space, and it's just going off in all directions. And that seems like the first way that we would be noticed by some sort of extraterrestrial civilization. This is the motivation for the whole class of programs that we call SETI, the Search for Extraterrestrial Intelligence. And the basic idea of SETI is you try to detect maybe radio or microwaves from planets around other stars that might have intelligent civilizations actively functioning in our galaxy today.
So this acronym SETI, the Search for Extraterrestrial Intelligence, it encompasses a whole variety of efforts and experiments. Basically, any scientific project trying to find intelligent life out there is called SETI.
So SETI, in at least some form, has a pretty long history. So back in 1924, there was this point in time where Mars was going to be closer to Earth than any time it had been for about 80 years. So it was announced that there would be this 36-hour period of time that was called the National Radio Silence Day. And in that 36-hour window, all of our radio signals were turned off for about 5 minutes of each hour. And the idea is if you could create this radio quiet period of time, even for a few minutes, you could point your radio telescopes or your antennas, I guess. They didn't really have telescopes to doing radio at the time, but antennas in the direction of Mars and see if anyone there were trying to communicate with us. Of course, no Martian messages were detected, but this kind of set off the idea of doing SETI. The first modern SETI experiment was conceived of in 1960 and led by the astronomer Frank Drake at Cornell. It was called Project Ozma, and the idea was to use the Green Bank telescope, which is in West Virginia. This is a big radio telescope, 26 meters in diameter, a giant antenna, basically. And they pointed this at two nearby stars. These stars are like 10 and 12 light years away, in the hope of detecting radio signals that might come from some sort of intelligent life. Again, nothing, of course, was found. These telescopes tended to focus on the frequency range of about 1.4 or 1.42 gigahertz for a couple of reasons. First of all, radio can penetrate the atmosphere, so you can do this from the surface of the Earth. You don't have to go into space. Human beings, at least, emit a lot of emission in the radio and as an effort to communicate. And it would be relatively easy to identify these sort of signals. They tend to be repetitive and narrow band, meaning they're in a narrow range of frequencies. And that's not what you expect of naturally occurring radio emissions. So there are at least some telltale signatures of a intelligent origin for radio signals.
So you may be wondering, is looking for radio signals really the most all-encompassing way to search for intelligent life? Is it, too human-centric to think that intelligent life out there would create the same kind of signals that we would here on Earth?
Yeah, no, it's a very good question, and it's one that like a lot of people have raised. There are a lot of reasons why a technologically advanced civilization you would imagine would emit a lot of electromagnetic radiation, including radio. It's one of the easiest ways to send lots of information through space. And that seems to be something that just about any advanced civilization would have used to do. So it wasn't just the Americans who were interested in SETI. The Soviets embarked upon their own SETI program in the 1960s. And you can imagine why. Like, human beings of any culture are going to be interested in this question. And, if you were the first superpower to discover intelligent life in the Milky Way, you might even imagine this would have national security sort of considerations.
Quick acknowledgement that in the year 2020, probably the last thing you want to worry about is the threat of aliens as an international security threat, but carrying on.
So in 1971, NASA funded a project called Project Cyclops. And this was a program to consider a possibility of doing an even more ambitious SETI program. The study concluded that the best way to try to do this was to try to detect electromagnetic signals in this gigahertz sort of range, so radio or microwave. And it wasn't cost effective. They decided to send probes or spacecraft into space to try to do some sort of SETI program. They thought this radio program was the right way to do it. And the design that they ultimately proposed consists of a plan to deploy a very large number of radio telescopes all around the world. And this would have been sensitive to Earth-like radio signals that were as far away from us as 1,000 or so light years. So this is a substantial piece of the Milky Way. It's a small fraction of the Milky Way, but there are lots and lots of stars, 10 million or so stars within this range. So you could look for intelligent life in a lot of different star systems. But this would have cost, they estimated, between $6 and $10 billion. And ultimately, no one was willing to pay for that. This was totally shelved because it was impractically expensive, or at least to the funding agencies at the time. And there's a long history of this sort of happening. SETI efforts get a little money, and then the money gets cut, or the program's being canceled because of budgetary considerations. And over time, there's been more and more of a shift in SETI efforts away from government funding sources towards private and maybe more stable forms of funding. A good example is this thing called Project Phoenix, using the Parkes Radio Telescope in Australia, along with the Green Bank Telescope in West Virginia. And they were looking for radio signals from roughly 800 stars in the roughly 1995 to 2004 time period. It's basically a Project Cyclops-like program on the light side. So not as ambitious as this 1971 NASA study suggested, but at the time it was still state of the art, and they could detect Earth-like radio signals from planets as far away as a couple hundred light years. Today, scientists are trying to do SETI in a bunch of different ways. They're using the low-frequency array in Europe, the MWA array in Australia, telescopes in the United Kingdom, the Allen Telescope Array in California, which is still being constructed, but parts of it are operational, and Serendip, which is a spectrometer at the Arecibo Observatory in Puerto Rico, along with the Parkes and Green Bank telescopes. All of these are actively doing SETI with at least part of their observation time. Roughly speaking, these telescopes are, trying to do this kind of state-of-the-art SETI, which would be sensitive to these radio signals out to about 1,000 light years, looking at maybe as many as 10 million different stars. That's a sort of sensitivity that these experiments or these telescopes are at least embarking on, if not having quite reached that goal yet.
Okay, so here's when we realize that despite all of these efforts over the years, we have not found a single hint of any intelligent life out there in the universe at all. Not one. So if we're serving 10 million stars, Shouldn't this be surprising?
Yeah, so like let's say, just to be concrete, that some years from now we've looked at these 10 million stars. We've looked at them with enough precision or enough depth to be sure we would know if they were giving off Earth-like signals, and we haven't seen anything. Is this a surprising result? Is intelligent life in 10 million star systems something we should have expected to find, or something we should have thought, no, there's no chance? And it seems to be a totally wide open question. But astronomers have tried to quantify this, at least try to, approach the question in a scientific way. And probably the most famous way of doing this is in something called the Drake equation.
So the goal of the Drake equation is to calculate the number of civilizations there are out there in the universe that we could potentially communicate with. And so it does this by basically multiplying a bunch of different numbers together, each number in the equation representing another thing necessary for this civilization to exist and be intelligent.
The first one is just the star formation rate in the Milky Way, which turns out to be, roughly 2 stars per year, something like that. Okay, so I've got 2 stars forming every year on average in the Milky Way. And then I ask, well, how many of those stars have planets? Now we know just basically all stars have planets. So that's like 100%. And then the next term or next factor in the equation is the number of habitable planets we expect around an average star. Again, Frank Drake did not know the answer to this when he wrote his equation, but because of modern observations of exoplanets, we have a pretty good idea. And it turns out that on average, a star has about 40% of a habitable planet, or on average 0.4 habitable planets per star. That seems to be about the right number based on our observations. So when we multiply that by the star formation rate, we're in the ballpark of about 0.8 habitable planets being formed in the Milky Way per year.
So we have our number of habitable planets. And next we need to consider the actual probability that each of these planets will develop life. This is a pretty speculative area because we really don't know the answer, but there are some educated guesses we can make. For example, on Earth, we know that the first forms of life, like those early microbes, those appeared very early in Earth's history, at least 3.77 billion years ago, and maybe even as early as 4.4 billion years ago. Given that the Earth is only around 4.54 billion years old, it seems like it doesn't actually take very long for a planet to develop life.
So, given the fact that life appeared, simple life anyway, appeared on Earth so quickly, we might be tempted to conclude that life, simple life, would emerge in habitable places very quickly elsewhere in the universe too. This isn't a proof, this isn't, a certainty, but I think it's at least a suggestive, notion. All right, so moving on. And if you thought the last factor of this equation was speculative, this one is 1,000 times more speculative. But this factor is what fraction of these planets with life will go on to evolve intelligent life. I have no idea what this number is. It could be close to 100%. It could be 1 in a million. It could be 1 in a trillion. It could be 1 in a trillion. I have no idea whatsoever. So this is going to be where our ability to predict these things breaks down, but at least we can quantify our ignorance. And then the next step in the equation, we're almost there. The next step is what fraction of those civilizations with intelligent life are communicating using radio. Again, we don't really know. I think there's good reason to think most might, but we don't really know. And then the very last factor is if they're emitting radio, how long do they do it for? Maybe that's a statement about how long the civilization persists, how long the species of these intelligent beings persist, or maybe it's just how long they keep their radio signals going. Maybe they evolve away and technologically away from using radio and using something else. Who knows? Okay, so now we take this whole string of numbers, we multiply them all together, and what we get when we're done is the number of intelligent civilizations in the Milky Way right now that are sending detectable radio signals out into space.
So with the Drake equation, we take how many stars are made in the universe, and then we consider how many of those stars have planets, how many of those planets can support life, then how many of them actually develop life, how much of that life develops into intelligent life and civilizations, and then we have to ask, are those civilizations around long enough for us to be able to communicate with them? And so there are a lot of factors here, and hopefully that's not too overwhelming, but the point is that defining all these different necessary steps helps us understand why we haven't yet discovered extraterrestrial life.
I don't think the Drake equation actually does what it's intended to do, which is give you a concrete answer to the question it's asking, like, what are the odds that SETI will succeed? What I think it does is it helps you understand if SETI does or does not succeed. It forces you to figure out why. So let's do an example. Let's say I'm an optimist about human civilization or intelligent civilization in general. In 2020, it's a little hard to be, but all the same, let's play that game for a moment. And I think that they're very long-lived. These civilizations, our civilization and many others like it, once they get started, they thrive for 1 million years. Okay. Or maybe 1 billion years, whatever, but let's just use 1 million. And let's say I also think that there's a 10% chance that once you have life somewhere, it becomes intelligent. It evolves to intelligence eventually. Maybe that's reasonable. I don't know. If I use the Drake equation, I multiply all these numbers together, what I find out right now is that there should be about 100,000 civilizations in the Milky Way that are currently sending out radio signals. And like 10 of them or so would lie within the reach of SETI, current ongoing SETI. So we haven't seen them. So at least one of our assumptions would seem to be wrong. So by using the Drake equation, I'm able to kind of pinpoint or at least narrow down what the explanations could be for why we haven't seen radio signals from intelligent extraterrestrial life. Another thing you might want to worry about is, like in 1 million years' time, if you want to be that optimist again, if these beings were traveling at near the speed of light, which of course, like there's no law of physics saying they couldn't, they could travel 1 million light years. And that's like way bigger than the size of the Milky Way. So you might have expected our galaxy to be teeming with outposts and, colonies of these hyper advanced civilizations all over the Milky Way. Even if they were traveling at like 1 to 10% of the speed of light, you'd expect this to be the case. Interstellar travelers should be a commonplace. So again, like we seem to, by not having detected anything, been able to learn something about the evolution or development of intelligent life and other places that we haven't been to. Let me give you an analogy. Let's say you're a member of an ancient civilization and you live in an island. And for the first time, the guy down the street on the island has invented a boat that's capable of traversing the ocean. Like this is a brand new invention. You've never seen this sort of thing before. You could use that information to ask the question, well, now that I know these things are possible, that boats could be invented, I can ask, like, are there a lot of islands like this inhabited by people like me? If there are, then there are probably lots of them that have these boats. I probably wasn't the first one to invent this. If there are lots of people like me on other islands, it's kind of weird. I haven't found seen a lot of boats sailing around, or no one's come and visited us. So maybe that tells me something about the scarcity of inhabited islands out there. Just in the same way, maybe by noticing the scarcity of radio signals that seem to originate from something intelligent, we've learned something about the scarcity of intelligent life in our galaxy. So let's say you were an optimist about civilization and its longevity. You thought that once intelligent life, takes root somewhere, it's, lives for a long time. After all other kinds of life seems to, there have been crocodiles on Earth for, hundreds of millions of years. So you might think naively that something like human beings will persist, or for hundreds of millions of years. I personally don't think that's likely, but so you can imagine someone who thinks that. And if that's the case, you could ask, well, like, why isn't our galaxy just teeming with, intelligent advanced civilizations? And this is known as something called the Fermi paradox. Enrico Fermi and Edward Teller and others in the 1950s had these conversations where they were like literally asking, like, given all we know about life in the galaxy, there should be lots of it and we should see all of it. And the question being, like, where are they? Where are the aliens? Why don't we see, the whole galaxy being transformed by hyper advanced civilizations? And I think the Drake equation helps us to at least like enumerate the list of possible resolutions. Like what's the explanation of Fermi's paradox? Well, maybe life is just a lot more rare than we might have guessed. Maybe the fact that, microbial life appeared on the Earth early in its history was just a fluke, a 1 in 10 sort of shot. In which case, maybe, life only appears, and even in its simplest form, once per galaxy or something, in which case there's no paradox at all to explain. Secondly, maybe, microbial life is really common, but there's some sort of bottleneck where, multicelled life is really rare. After all, it took a long time before multicellular life appeared on Earth. That hadn't appeared on Earth until like 600 million years ago or something. So it's possible there's a real bottleneck going from single-celled life to multicelled life. Or maybe there's a bottleneck going from not very intelligent multicellular life to the kind of intelligent life that could build, technology and, lead to the sort of things that we're talking about looking for with SETI. And the third possibility is that technologically advanced civilizations might not last very long. I think there are a lot of reasons to take this option seriously. I mean, 100 years ago, I think there wasn't any particularly good reason to think that human beings were about to develop technology that would make their civilizations perilous or imperiled in any serious way, in any existential way. But then nuclear weapons and bioengineering and effects on transforming our climate, stuff, and not to mention stuff we haven't thought of yet. Personally, I'm really worried about artificial intelligence as a existential danger to humans and human life.
So maybe intelligent civilizations just tend to annihilate themselves, maybe with artificial intelligence or climate change, before being able to leave their home planet and explore the rest of the galaxy. Or maybe it's really just that difficult and unlikely for nature to end up developing intelligent life. And we're just lucky to be alive and sentient here on Earth.
Now, so far in this discussion, everything we've said has been about our own galaxy, or even just like the 1,000 light years around us that we can like look for with SETI programs. But I think it's worth keeping in mind that the Milky Way is only about 1 in a trillion or so galaxies that reside within the observable confines of our universe. So even if, we're about to destroy ourselves as a civilization, we're typical. So there's like 100 years of radio heavy transmission from each civilization. So just to be really pessimistic. And let's say the odds of intelligence emerging from simple life is like 1 in a million. Even if that's the case, there should be something like 1,000 intelligent civilizations in the universe right now. As large as this probability of intelligence emerging from life is larger than roughly 1 in a billion, we probably aren't alone in the universe.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.